How's it going there, Dick? I looked at some of your images and it inspired me to try to do some of those same targets, like the Galaxy 7331 and Pegasus
Oh yeah.
and Stephen's Quintet and all of that. I did those back in early October.
Did I mention that Messier missed that one? It's,
Yeah, that's
it's nicer
surprising.
than many of the Messier objects.
Yeah, it's pretty bright. I heard it was the brightest galaxy in Pegasus. You
Well, I
know?
like it because it's high in the sky.
Yeah, I know. It's really nice. You get out of
All
all
these
the
trees
muck.
around here, I need hot stuff that's high.
Yeah. Yeah, I have a little, I don't have as severe a problem as you do, but I do have my southern horizon. There's a little gap in the southeast that goes down to about minus 25, but it lasts about an hour and a half. And then I'm stuck to about minus 10 as low as I can get, you know, and probably just a little past zenith in the north.
We had a bunch of trees taken down, especially in
Oh,
the south.
really? Okay.
Yeah. So now we can get to minus 10
Oh, there you
for a couple of
go.
hours. So you're going to be seeing some objects down there shortly.
Yeah. Yeah, you're on the cusp of getting some of those Sagittarius because that's
Oh
about
no,
minus
I'll never
20.
get
It's
to
minus 20.
Sagittarius.
Yeah.
And we got neighbors' trees. I can cut our trees. I can't cut our neighbors' trees.
Yeah, that's the problem I have. The tree that's giving me the biggest problems in my neighbor's yard. It's a beautiful tree, but it is, unfortunately, if it was
No.
set back 50 feet further, it would be a lot nicer. Give me a lot
You may
more.
have noticed in my images that there's a delay, a couple month delay. Like, M31 is really up for everybody now, but for me, no. It's I got a giant oak tree blocking M31, so it has to wait a couple months or at least weeks, a few weeks.
Yeah,
That's just the way it is.
yeah.
You can't take down a 200-year-old oak tree.
Yeah, that's the thing. My neighbor has an old oak tree too. It's very old, and it's a beautiful tree, but it does limit me a bit.
Yeah. This Pittsburgh thing sounds pretty interesting. I don't know if they can make a dent, but it would be interesting to see a before and after that if it actually makes a difference in trying to maintain dark skies.
Yeah,
I'm not optimistic, but maybe a little bit.
Maybe.
yeah. Every little bit helps.
Are there a bunch of clubs out there?
A bunch
Yeah,
of what-
there's a huge one. Yeah.
I mean, they
Pittsburgh-
should
The main
start
Pittsburgh
doing,
club is like well over 300 people.
they should start doing like sky readings now. And then as it progresses, just to see if it really does change or not.
Well, the person that spearheaded it did a lot of research with drones and try to document where all the bad light pollution was. So I'm sure she's going to follow the progress.
Oh,
It's
great.
really interesting to read about.
Make it easier to see Starlink.
Right?
We don't have an observing report tonight, Jeremy, so I think we have to have our speaker before we get started.
Yeah,
How will we know when the speaker is around? Well, no, my screen's full. It says
It's page
29
two.
participants.
There should be a little triangle to the right.
5, 10, 15, 20, 25 fit, but not 29. There's 30. Somebody just joined. See, there's a little number next to participants. It must be
Yeah,
30
yeah.
now.
If you click on that, it'll give you a list.
Oh. Oh, yeah. Okay, I see.
I don't see him yet.
Well,
What's the speaker's name tonight, Jeremy?
John Conrad.
Yeah, I don't see him yet.
Send him an email now in case he's having trouble finding the link.
Hmm.
He's given a few good talks in the past there, you know?
Yeah.
Wonder how his ankle's doing.
uh-oh, I just did something bad.
If that's been about 2 years, all right?
I think so.
Yeah.
Because it's been almost 2 years since we've been at Radnor.
There he is. Is that? No, that's not him.
Well, yeah, come March, there'll be two, right? Yeah. Or no, wait,
The
Oh.
last one was February of 2020.
right, the last in-person
One-
meeting
Yeah, March was the one
at
we had,
Radnor.
like the day of.
Are we thinking about going back in January, or is that still up in the air?
I guess we'll just have to play it by ear, but I think that's kind of the plan. Have you talked to anybody at the at Radnor, Jeremy?
I mean, the room is open and available if we want it.
Okay,
They're holding their township council meetings there. You can see on YouTube, they've got all like the plastic barriers set up between the seats in the front.
hmm
They have the chairs all spaced out.
Now, are they requiring masks for the meeting, or, oh, here he is now.
There he is. I don't know, the recordings I saw, there were some people not wearing them, so I don't know. Maybe they
It's-
are
it's-
requiring them, but some people are ignoring it.
It's either optional or whatever, okay.
Yeah. Or it's required, but somebody's got to show up with a stick to enforce it.
Right,
Nobody wants to. Hey, John, welcome aboard. Oh, you're muted. You got to unmute.
there we go.
How's that doing?
Yeah,
There we go.
Good.
How you doing, Jeremy?
good, good. How are you?
Good.
All right. You ready to get started up?
Mm-hmm.
All right. You want to take it away, Jan?
Sure. Hello, everybody, and welcome to the October monthly meeting of DVAA. My name's Jan Rush. I'm the VP of the club, and I'm sitting in for Harold Goldner, who had another commitment tonight. So, looks like my screen is not full screen. So
Do the from beginning.
what did I, yeah, that's what I hit. There we go. All right. Excellent. So welcome, everybody. I think this is a fortuitous time to have a meeting, because as I was looking up what's happening in the next couple of days, we have a speaker who's going to talk about the launch of the Lucy mission, which is imminent. It's going to be, I guess the first day for the launch window is tomorrow morning at 5:30. So here we are, a very timely speaker and an exciting mission about to begin. And when I was looking at the information on this mission, these are the things that kind of blew me away. First of all, and maybe John will elaborate on some of these or all of them. And if he doesn't, I'll ask the question when he finishes. Supposedly, this is going to travel farther from the sun than any previous solar-powered mission, and that's kind of cool. The Trojans that Lucy is going to visit are asteroids that are primordial rocks from the very early days of the solar system, which were conveniently captured by Jupiter, where we can actually reach them. And this one, I don't know if this is just NASA hype or whatever, but hype is that after visiting all the planned asteroids, Lucy will remain in a stable orbit for an additional many thousands, perhaps millions of years. I think that's NASA hype, but John, make sure you set us straight on that. Okay, so let's do some regular committee reports. Brian is our welcoming chair.
We have 6 new members this month, William and Lynn Wassel, Corinne Simmons, Mohammed Osman, Teha Berberich, and John Rowan. I did not see any of them tonight here, but if they are here, welcome, and thanks for joining.
Yeah, I didn't see Lou join. He's not on, is he?
I don't believe so.
Okay, so I'll say a couple of things from the treasurer standpoint. First of all, we now have 207 members, which is a great total. Everyone who joins between now and the end of the year gets an expiration date at the end of 2022. So you get a couple of extra months there. So if you've been thinking about joining but you didn't want to because it was the end of the year, well, you still can. With respect to outreach, we have a couple of things on the calendar. In the table at the bottom, you can see there's 2 remaining public star parties. Not looking too good for tomorrow night, but if we can get rid of the rain early as possible, maybe. But tomorrow night's a Valley Forge Star Party, and then on the November 13th will be our last one. We have 2 outreach events that are remaining this year. One on the 19th of October at Anderson Farm Park in Upper Providence, and Alan Lamperti's in charge of that one. Is Alan on the call? No. The last I heard from him, he was good with volunteers. He has enough people. And the same with the Girl Scouts of Royerford oops, I didn't want to turn that yet. Girl Scouts of Royerford on the November 10th. I believe he has enough people for both of those. And I have an announcement to make about outreach. One of our outreach stars is going to take over as outreach chair for the coming year. And that's Roy Patton. And he really is an outreach star. He's been to more meetings or more outreach events in the last 3 years than probably anybody. So he and I will be getting together to talk about transition. And we actually have a couple of events lined up already for 2022. So we're off to a good start, and we're recovering from the pandemic, I'd say. Did you want to say anything, Roy?
Just, I hope to follow in your footsteps as well as I can. You've done a great job, Jen, and it's going to be, I'm going to need your help every once in a while, just to keep things.
And it's always great if the people on the call can be interested in learning about outreach and volunteering, because we can always use more people. And it's a lot of fun, actually. I think those of us who do it really enjoy it.
Oh, I love doing star parties. Just watching people's faces when they see something for the first time is just
amazing.
The best. It's just the best thing.
Right.
So
we had 2 very different events on October 1st. There was one at a fundraising gala where they fed us drinks and hors d'oeuvres the whole time. And on the same night, there was one at an elementary school that was apparently a real zoo. So
we got the right one.
We got the right one. Okay. I also want to talk about our beginner and intermediate clinics. And these have been lots of fun. Everybody that signed up to help is actually happy to do another one. So I know it's a great place to have fun and meet people. So we're going to be doing one on December 5th. And I invite everyone who's interested to sign up for that. So what happens at a telescope clinic? Well, it's a great way to informally get to know other telescope enthusiasts. If you would like hands-on expert help, we offer that, and by collecting information before the clinic, we're finding out exactly what telescope you have and what your questions are, so that we'll have someone there to work with your specific scope and with your specific scope. And this time we're also going to do a laser pointer tour of the season's constellations. So it will be a good time to talk about what the best targets are for the fall and winter season. And we'll be pointing out exactly where the targets are in the constellations and how to find them and practicing doing that. And we'll have hot coffee and cider because it'll be cold. So this clinic will be right now scheduled for December 5th. Of course, that's weather dependent. It's at 4:30 to 7:30 because sunset's pretty early in Hebner Park in Worcester Township, which is where we've had the previous similar events. And there's plenty of time to watch the Eagles game and then get there. So we'd like everybody who'd like telescope help to register ahead of time so we can make sure to have the right people there to help with the telescope that you're bringing. And anyone who would like to help out at the clinic who hasn't already told me, please send me an email and I'll get you on the list to be an expert. And last thing I wanted to mention, we don't have an observing report tonight because Andrew's away, but if you haven't thought of it before, think about our rental telescopes. These were all new in less than 2 years ago. They come with information on each telescope and everything you need, eyepieces, tripod, manuals, books, everything you need. Rental for members is $10 a month and with a $20 deposit, which is refundable when you return the scope. And if you'd like to rent one of the scopes, talk to Joe Lamb. There's his friendly face there, and he's happy to help you out, and he'll explain the scope to you if you don't know much about it already. I'll tell you, what's clear from the telescope clinics is that a lot of people who are looking for a new scope have some angst about what kind to get, and renting one and trying it out ahead of time really can help you firm up that decision. So if anybody's in that situation, I urge you to give Joe a call. Okay, as I mentioned, we have a great speaker tonight, so timely. Jeremy, thank you for this scheduling coup. As I said, we'll be hearing about the Lucy message, and I'm going to turn it over to you, Jeremy, to tell everyone about it.
All right, thanks, Jan. Yeah, we're really happy to have John back here again. You may know John from some previous presentations that he's given. So John is a NASA JPL Solar System Ambassador. His background is in space and space flight. He has degrees in astronautical engineering from the U.S. Air Force Academy and Purdue University. And he spent his career working in the unmanned space programs for the U.S. Air Force and for NASA. And since retirement, he's been very active in outreach and astronomy. So John has given us several presentations in the last couple of years. These include climate change, the view from space, lunar science, and what we've learned from the Apollo program, as well as Cassini and the latest science from Saturn and Titan. So tonight's talk, as Jan said, is especially timely with the Lucy mission, hopefully launching tomorrow. So actually, we're going to hear about it tonight. So please join me in welcoming John Conrad back to the DVAA. I think you're muted. We can't hear you.
I am an engineer, or I should say I are an engineer. So I'll catch on to the controls in a minute. It's good to see all of you again. And I really look forward to, sort of walking back and forth in front of you. I enjoy that much more. So hopefully when we can stop being so careful about these things, maybe in a year or so. I look forward to seeing you, but thanks for having me. And this Zoom situation works very well. I'm going to put myself over to the side here. I'm going to share my screen and get started here in just a second. So how's that coming through?
Yep, we can see it.
Okay. Getting something out of the way. For some reason, there's something. Zoom's always got something else that you have to click off, it seems. All right. So as Janet so clearly said, we are in that amazing position of being literally within hours. We passed the 12-hour point a couple hours ago before the launch of NASA's next great robotic spacecraft, Lucy. The launch window actually is quite flexible. Tomorrow morning at 5:34 local time is the first opportunity, but there's another one the next day at the same time. So it's quite likely it'll launch this weekend, but if weather or whatever keeps it from launching, there are a number of other launch dates coming up soon also. So we're talking about a spacecraft that has been managed, and the mission has been managed by, and now I need to get my clicker working, there we go, by a PI, a principal investigator at an organization that you may or may not be familiar with. They've been quite useful for spacecraft programs for quite a long time. I believe New Horizons is from Southwest Research Institute, as well as Juno, which is currently orbiting Jupiter. Hal Levison, Dr. Hal Levison, is pretty close to being a contemporary of mine. He's been at these things for many decades, and he's been about as approachable and helpful a NASA supporter of sharing information for the ambassadors as anybody. So he's talked to us several times in the last couple of years. I've actually exchanged emails with him in the last week to get a couple questions answered to cover this. And so I wanted to give credit to Hal and note that quite a number of the slides are his. They were really good PowerPoints. So I wanted to talk also to give credit to the people in the lower left-hand corner there. NASA Goddard is actually the center down in Maryland that manages this mission. While you may think of JPL out in California, they do manage most of the deep space missions, but NASA Goddard has this one. And Lockheed Martin, my old alma mater, is the spacecraft builder. And the three organizations across the bottom, Applied Physics Lab down at Johns Hopkins, Arizona State, and Kinetics are suppliers of the instruments for Lucy. So Lucy's an interesting name. For once, it's not an acronym. It's a name that is brought about by a reference to this collection of bones that you see here. You've probably all, if you pay any attention to scientific things at all, seen this before. It's not just an actual image of a bunch of the bones of an early human ancestor. It's also kind of a logo for fossils at this point. Discoverer and his team, Don Johansson in Ethiopia, had this find in 1974. At the time, I don't believe anymore, but at the time it was the earliest, how do you say it, Australopithecus human ancestor that we had discovered. I think there may have been others since then. At any rate, it's quite a fossil and been very famous. And NASA has chosen to name the mission that because NASA is all about visiting fossils that aren't on Earth, that are across the solar system. And so that's where the name comes from. You might wonder where Don Johansson, the archaeologist, got the name. He said that their team loved Beatles music and they were listening to Lucy in the Sky with Diamonds a lot. And that's the namesake. NASA decided that they liked that little story as well. So they took the diamond and decided to make it the shape of their logo for their mission. So there you have it. All right, so next is a look at the solar system's fossils. Obviously an artist concept from what we believe to be the structure of the rotating and collapsing disk that was the beginning of the solar system about 4.6 billion years ago. And so after the sun had lit up in the center, the disk of gas and dust was collapsing down under gravity as the sun had. And the smallest particles, the grains and gas, through some process that we don't fully understand, become fragments that get named planetesimals if they gain any size at all. And so the early solar system is an unbelievable amount of a disk of these planetesimals and dust and grains reaching way, way out. And what happens in every star system is at some point, planets begin to form, and as they form by the gravitational attraction of the planetesimals and collapsing in on themselves, they sweep up all the material in their particular distance out from the star. And so you see those lanes. And so it's a very early beginning in the first 100 million years or so. And what I want to point out is the more collisions, the more collapsing, the more fragments that are formed from smaller fragments, the more compression there is, the less like the original primordial material do you have. And so what we want to try to get back to is the very earliest material in the solar system. And so we're going to look for where that is, and we're going to talk about how Lucy is going to be the next visitor to some of that. So here's yet another artist concept looking down on the solar system with the sun in the center, and 1, 2, 3, 4, Mercury, Venus, Earth, Mars. And then you've probably already figured out that mass of objects out there are actually the asteroids in the main asteroid belt, with some that have deorbited mostly through the years from that belt through collisions, which have removed energy from an object and put it into a lower orbit around the sun, many of which have become what we have talked about as the near-Earth asteroids. At any rate, these asteroids have actually undergone quite a bit of change from the material, but there are in the asteroid belt many more original primordial materials, and the comets and asteroids themselves are much closer to the origins of the solar system than the planets. And so we've always expected that since they can be considered to be early fossils, they are going to tell us something about the formation of everything else, but especially the planets. And as we look at where they are in the solar system, here's a chart to kind of introduce the positions of everything within 100 astronomical units of the sun across the horizontal axis there, the x-axis. So you see one by definition is the distance from the Earth to the sun, that is an astronomical unit. We go out to 10 and we get quite a few more planets, and out to 100 and we've got them all. So that's what that axis is going to show us. The y-axis is the eccentricity of the orbit. And so as Kepler gave us in one of his laws, the planet's orbits are all ellipses, closed ellipses, and they are of varying eccentricities, where the term sort of in an intuitive way means if it's squished some and not perfectly round, then it's getting to be more and more eccentric. So if you have zero eccentricity, you actually have a circular orbit. And so down there in the lower left is an example of what a circular orbit would be on this chart, close to the sun. So here we have the location of these 8 orbs, which you recognize as the 8 planets. And most of them have a low eccentricity, especially Venus and Earth, and way out to Neptune there. And the most eccentric is Mercury, but it is not by no means oval shaped enough to cross over into Venus's orbit. So that's what we are well aware of as we move out from the sun to about 30 AU, where the furthest of the 8 planets is. And then we've got the rest of the solar system, and all of these, what are officially and formally known as small solar system bodies or dwarf planets. And so you see some of those other orbs, and we'll talk about them in a second. Those are the dwarf planets. But the colored things here are all of the small solar system bodies, which of course you're aware, looking between Mars and Jupiter, is to a large extent in that main asteroid belt. And you notice that that's where it is in terms of distance, but many asteroids get towards higher and higher eccentricities. And so you have quite a spread of out of roundness there. And then you probably already know about what's beyond Neptune, the trans-Neptunian area of the solar system. The Kuiper Belt, first of all, which by definition goes out to about 50 AU and contains most of the dwarf planets like Pluto. But then as you get to further and further out of roundness, further elliptical stretched orbits around the sun, everything's going around the sun, then you find this cometary area, which is further out there beyond the Kuiper Belt for the most part. And that is the origin of the very elliptical orbits of the comets, which come in around the sun. Many of them get close in, some of them don't get all the way there, and some of them, if they're more circular, stay well out at those distances. So those are a lot of the fossils, and yet there's this green group right in the center crossing Jupiter's orbit out from the sun. And that particular group is the Trojans, and that's what we're going to talk about as our target. And so we would like to visit these fossils because, or these areas of the solar system, because they are the places where the material that's the most primordial still exists, and it could help us understand planet formation. And so let's talk about whether or not we can go there and what we can learn. And as it turns out, there have been lots and lots of missions, as you're probably aware, to the asteroids. Along the top there, you see a number of missions to the comets coming in as the dashed lines show from their point of origin in the scattered disk, the eccentric orbit region of the furthest out part of the Kuiper Belt and beyond. And not all these are NASA spacecraft, as you probably noticed. The Japanese have been very successful with Hayabusa and Hayabusa 2. They've actually been the only country that's brought back some asteroid material to the Earth, sample of it. The Chinese are also on here with Chang'e 2 up towards the middle there. The latest NASA spacecraft to get a fair amount of press last year was OSIRIS-REx. And OSIRIS-REx visited, as you can see by the arrow there on the left, it visited an asteroid known as Bennu, which is a near-Earth asteroid at the same distance out from the sun in a slightly eccentric orbit there. And as you can see, its origin, we believe, was the main belt. It deorbited at some point when it lost energy. So that's where we visited there. We've also more recently, as you're aware, with New Horizons, had two very special visits with the last of what used to be the planets, Pluto, followed by a selected item in the Kuiper Belt known as Arrokoth, which we'll see in a few minutes. So we've been getting around in terms of studying the older things and the fossils, and yet we haven't gotten to the Trojans, but Lucy is going to do that. And as you'll see, it's going to do it with a number of observations. And so finally, we'll get to the last remaining opportunity to look at some of the oldest material in the inner solar system. It's, I think, important to understand where the material comes from also, to think about, again, that question of how much has it changed since the beginning of the solar system. And so the things that are in the asteroid belt were in the region of the terrestrial planets and the inner solar system, where there was a lot more of rocky material and a lot more planetesimals and collisions and changes especially in the case of some of the larger asteroids like Ceres, where they changed a lot with the collapse under gravity into hydrostatic equilibrium in order to become spheroidal or at least somewhat round. So the material in the main belt, which is not shown here, is much more changed than the outer material, which is shown here beyond 15 astronomical units. So if you're at all familiar with distances and the arrangements of planets, you'll be aware that this order, Jupiter to Saturn to Neptune to Uranus, isn't correct for today. And as a matter of fact, the outer ice giants there, Neptune and Uranus, are in the other orbit, in the other order, and are much further out than shown here. And so what this is going to be a quick animation to show you what we believe happened in the first 100 million years or so of the solar system. And it's been simulated by a number of different research groups, but the one that has had the model that's held up the longest is, it's known as the Nice model. Looks like nice, pronounced Nice. A couple Europeans, and the other member of the group is Hal Levison, the PI for Lucy. I was really interested in his talks to us to learn that back in 2005, he and the other scientists published what today is still believed to be the best guess at the early solar system evolution. So I won't jabber on anymore without showing you the animation. So here's what they believe in a very simplistic form is what took place over a period of tens of millions of years, probably. The outer ice giants were pulled in by Jupiter and Saturn's gravity, which is, they are much bigger than the outer two. And so as they migrated inward, then they were repelled outward. And as Saturn and Jupiter settled in, and as they went out, Neptune was actually kicked past Uranus. And a lot of that cold material was scattered in many directions. So I don't expect you to remember that. I'll just take you back to it for a second so you can watch it again. So you'll see Neptune come towards Saturn, be pulled backward, and then cross over Uranus, and watch what happens to all that material in the furthest out part that is the least changed of the solar system. You see it being scattered. Most of it was actually scattered out of the solar system into interstellar space. A lot of it became the Kuiper belt and the scattered disk, and some of it was scattered inward and went into harmonious orbits, if you will, at the same distance out from the sun as Jupiter. And we'll talk about that now. And we'll take a look at it. Here is the animation of the inner four terrestrial planets. And between Mars and Jupiter, the orange one, we don't show the main belt because it would clutter it up, but we do show the location of the two swarms or camps of the Trojan asteroids as they were captured at that particular point after being brought in from further out in the solar system, and where they've been for well over 4 billion years. Very stable orbits. You may or may not remember that we talked about this particular stability, but I'll give you a reminder here. Astronomy is all about math, among other things. And really, since the 15th or 16th century, since it was sorted out how not only how gravity worked in the 17th century, but how the sun is at the center of our local quote unquote universe and not the Earth. And so once we sorted that out, made observations, and Kepler and Newton and others who were also great mathematicians figured things out, there were some classic problems that arose. And one of them was known as the three-body problem, which simply is, in the case of the astronomy, in the case of astronomy of any star system, is if you have the central attraction and you have major bodies that are in orbit around that attractor, are there any places that will feel the gravitational pull of both the strong central attractor as well as the planets pretty much equally that are stable? And Lagrange worked on this for a while, and it was a really incredible solution that he came up with 5 stable solutions, which we now know as the 5 Lagrange points. 3 of them are collinear with the 2 bodies. Picture the sun in the center, and that gray body could be the Earth or Jupiter or whatever. And if it was the Earth, you could picture L2 and remember that James Webb Space Telescope is going to be out there in a nice stable configuration. But the orbits that lead and follow by 60 degrees, the second major body, are known as the L4 and L5 points. And those are very stable, and they're known as the equilateral solutions to the 3-body problem. And so Lagrange solved it. Eventually, we had telescopes that were good enough to look there. And lo and behold, in the 20th century, we found these Trojans. Trojan, it turns out, is not just a Jupiter asteroid word. It's a generic term. And so we can find Trojans in any 2-body system looking for some stable third bodies. And we've looked in the different planets to the extent that we can. We found quite a number of Trojans in the Mars system, and we've actually found 2 now in the Earth-Sun system. Again, at 60 degrees before and 60 degrees after the planet as it goes around the sun. Now, I want to point out a couple things here. One is that you think of Trojan asteroids because that's what you'll hear in the press, and that's what you probably learn in a science class. But the fact is that they aren't as near to Jupiter ever as the Earth is sometimes in its orbit. So that's one thing to think about. Another thing is to see the size of these swarms, and you'll see how that's used as we put a spacecraft up there to actually fly by and take a look at some of these. All right, so finally, before we get into the actual planetary orbit, I just want to highlight the fact that in terms of fossils, we're going to be looking at material in the Trojan asteroids that's quite different than what we found in the main belt. Low density, volatile rich, what you expect from material that comes from the colder regions further out. And our observations, and we've had many, many Trojans that we've now observed, especially from Hubble. As a matter of fact, they've been able to estimate the count of one of these swarms as being 600,000 or more. And that means that the whole set of 2 camps of Trojans is over 1 million, we believe. So it's not like they're a small group. But at any rate, they're very inhomogeneous. And in one sense, we refer to asteroids by how gray or pink or red they are. And in the case of the main belt, most of the main belt asteroids are gray asteroids, which are the C type of spectral coloring. The reddest ones are known as D type asteroids, and they're redder than Mars. And kind of halfway in between are the P type. And so this little graph here just indicates, these pie charts indicate that across the range of sizes of all the Trojans that we've observed, there are very few that are like the main belt, that are the gray C type, and about 7% they've estimated. And the rest of them are split about 50-50 between P type and D type. Another, if you will, inhomogeneous. Did somebody ask a question? I'm going to stop in a minute and give people a chance to ask questions if you have any. The another type of spread inhomogeneity is in terms of the reflection of these bodies, how reflective they are. And albedo is the useful measure for that. You've heard of the moon's albedo, and it's why we are able to see Saturn and Jupiter and so on. Reflected sunlight And in the visible, with the eyeball, visible albedo in terms of the Trojans is maxed out at about 15%. And so it's not like they're bright. It's just that many of them are much brighter than others. So they have a range of brightness. 15% albedo is about the same as asphalt. And so we're going to be looking, or the spacecraft is going to be looking to find and center on specific targets that are, that particular range of reflection, asphalt and darker. So with that in mind, I will pause for a second and ask if there are any questions so far before we get into the spacecraft's trajectory. Anybody? All right, we'll move on then. Another simple picture so that we can concentrate on the things that matter. Just Earth's orbit and Jupiter's orbit shown, and sort of a little clever little drawing of where the targets are before and after Jupiter's orbit. On the right there, you see the launch vehicle, and it's an Atlas vehicle. As you're aware, they're very long in the tooth. You may remember that they came out of the Air Force's development of an intercontinental ballistic missile in the 50s. So the Air Force was about 5 years old when it was developing the Atlas, and the Atlas now is about 70 years old. In the 50s, we discovered that it couldn't just go from continent to continent, it could also go out into space. So it became the Space Launch Vehicle 3 is what it was called when I was in the Air Force in the 60s. I launched one in 68. And so there have been many variations of them since, and the inventory is down to the very last few. And here is one that's going to launch Lucy. And it's notable in that it's not a very powerful rocket compared to many these days. And that was in order to keep costs down and to take advantage of the fact that the astrodynamicists in Lockheed Martin, I believe, maybe also in NASA, had come up with an extremely clever orbit to take advantage of gravity assist to get the payload all the way out to the Trojans. And so tomorrow morning, 6 hours, what is that, 8 hours from now or so, hopefully there will be a launch. If not, maybe the next day. And so Lucy will be off, and let's take a look at what that looks like from the launch, as you see there from Earth with this animation. And so it goes into a low Earth orbit for a year. And it's quite an eccentric orbit compared to Earth's. In order for it to come back at what will be the perihelion then of the next orbit, the closest approach to the sun, as it now gets a boost from Earth's gravity. And the way that works is simply Earth rotates. It's got a lot of gravitational energy. And if you play it right, you actually borrow some of that energy and put it into your own orbit as you go by. And it does slow the Earth down, but I would defy you to tell by how much. At any rate, it kicks it into a higher orbit. And that orbit, it turns out by design, is a 2-year orbit this time, until it comes around one more time for another gravity assist. And that'll take place at 3 years out with another boost. And this time it boosts it enough to give it the energy that will take it all the way out in an elliptical orbit to Jupiter's orbit. And so here it goes on its 3 hour, I should say, 3 year orbit out to Jupiter. On the way, again, by design, they knew they were going through the main belt. And so they picked an asteroid to practice pointing at and testing the instruments on. It's, as it says, MBA rehearsal, main belt asteroid rehearsal. And the asteroid they picked just happens to, in 2015, been renamed Donald Johanson, who was the discoverer of the Lucy fossil. I suspect that that was a result, not just a coincidence. At any rate, so they're going to go by Don Johansson. It's not a scientific visit so much as just a test, and continue out on 3-year outward bound part of the orbit to Jupiter's distance from the sun and the first of the Trojans. And so here they are at the L4 swarm and the first flyby of a Trojan asteroid known as Euripides. And just recently they discovered that there's a small moon going around Euripides, which they've named Quetta. And you see that they are C-type. They're the unusual gray ones, more like the main belt asteroids. And in this case, as I'll tell you in a few minutes, it's also, Euripides is also unique in another way. But at any rate, that's the first visit coming up in a little less than 6 years from now. The first 3 years were in the first 2 gravity assist orbits, and then 3 years on the outbound leg of a 6-year orbit that's going to come back in. And then it goes on through the swarm. The second target, a month or so later, will be a P-type, a pink one, Polymele. Continuing on in the swarm, then it gets to Lucas. In this case, another, or I should say a red one, a D-type. And then finally, a fourth encounter in the L4 swarm with Orus. So in that period, which lasts about 15 months, they will actually visit 4 target Trojan asteroids covering all the spectral types, and now be headed back in as gravity brings it on its closed ellipse back to Earth again, perihelion. And this time the whole orbit will be rotated slightly so that it will intersect with the other swarm. And so as it goes back out 3 years later, it will reach Jupiter's distance, and it will get to this very interesting pair of large asteroids in the L5 swarm. And at that point in 2033, 12 years from now, and here it is as it reaches its what's called the aphelion, the furthest point from the sun, it will be through 1.5 full elliptical orbits out to Europe, or to Jupiter, and it will have covered all of these target asteroids and be quite a rich take and the end of the primary mission. And when I say at the end of the primary mission, it's because, again, as Janet pointed out earlier, by no means will this be the end of Lucy's life, just the end of the first time out to all these things. Because the orbit that they're putting it in, which you see in this animation here, being half the time of Jupiter's and therefore the Trojans' orbits around the sun of 12 years, will cause it to synchronously reach out to and get to, if you look at this long enough, you understand that the front end of the leading swarm is where it arrives, and the tail end of the following swarm is where it arrives, in order to have that 6 versus 12 frequency work out for these visits. They've done the simulations on this, and as you're aware, when you're in space with gravity, the only force on you, if something else doesn't come along to perturb it, it just keeps going that way. And they've run it out past 100,000 years, and it looks like it's just going to keep going like this. The power on Lucy is such that it will continue for a very long time, as long as the instruments are as successful as we hope. They'll be gathering data for a very, very long time with the Lucy Trojan visits here. All right, before I go on, are there any questions about the trajectory, the orbits? And I do appreciate somebody, moving a chair or coughing once in a while. Otherwise, I feel like I'm sitting here talking to myself. So,
John, this is John Moran here. What is the risk of it hitting miscellaneous particles out there? Seems to me to be pretty high.
Okay.
the distances between these objects are enormous.
Okay.
you picture Han Solo flying into the asteroid belt or whatever that was, and going inside the the dinosaur or whatever he was at some point, the dragon. At any rate, that rendering of all these asteroids in a belt that you can almost run into if you aren't careful is completely erroneous. It's said that you almost can't see any other asteroid from any of the asteroids if you just were on one and looked. These are very far apart. There will be probably plenty of micrometeoroid collisions, and we'll talk about that in a minute. But it's a very low probability it's going to hit anything. Anybody else? All right. So as I said, the first move out, and after the first half of the elliptical orbit, the first 3 years that gets out there in 2027, 6 years from now, will give us this very big take from the L4 swarm in only 15 months. The next visit that will come years after that, 6 years after that, 12 years from now, will take us to these. And so we will have covered both swarms and all known spectral types, C, D, and P. And let me note some special things about a couple of the targets. Euripides is very unusual in the Trojan asteroids, but wouldn't be at all unusual if it were in the asteroid belt, the main belt. The main belt, as I said, has had a lot more collisions, a lot more movement away from the undisturbed state in terms of many of the asteroids since the beginning of the solar system than the Trojans and certainly the Kuiper belt. In the case of Euripides, it's one of what's called a collisional family. I've read, and it surprised me, I just read it recently, that the main asteroid belt, most of the asteroids are parts of collisional families. And the reason they can plot these families is basically by plotting all the orbits and looking at the similarity of the orbital elements and being able to see that most of what they see are traveling together as a family, which they deduce to have been caused by a collision at some point in the past, with larger objects becoming smaller objects. And so again, more disturbance, which has changed stuff from the original. In the case of the Trojans, they've looked and looked for collisional families, and they've only found one. And Euripides, hello? Question? I'll go on. And so Euripides, they've targeted as the largest member of the only known collisional family, which means it's going to give us an interesting look at how the material in the Trojan belt or the Trojan swarms have changed since earlier, since it is changed. The others they believe to be unchanged. Is there a question? Somebody has their mic open.
Sure, cancel already?
Okay.
No, it's okay.
No, I checked it though. I didn't see it. I really did check around.
Hello.
Shoot.
I guess I'll just go on. In the L5, the target there are very special. Patroclus is actually the second largest objects they've found so far in the Trojans of the hundreds of thousands. Menetius is its partner as a binary, very close to being equal mass pair, rotating around a common center. They've observed it long enough. You can see the Hubble Space Telescope actual image there in the upper right, but the period is 4.3 days, and each of them are well over 100 kilometers in their longest axis. And so, as I said, Patroclus is the second largest we've found so far. The reason they're particularly excited to see this pair is because they believe they are really, for sure, among the earliest objects in the solar system. And the reason they say that is they've been studying in the Kuiper belt for many years what are called cold classical KBOs. equal mass binaries. They've found a lot of these, not in the inner Kuiper belt, but maybe beyond 50, AU. You see some images of some that they've seen there. You see an equal mass binary or a near equal mass binary in the lower right that you may recognize. It's actually known as a contact binary, not quite enough energy, if you will, to pull the two apart, and not quite enough to actually push them together any more than touching. That's Arakath, and that's what we visited with New Horizons about 2 years ago. And so these equal mass binaries, being many in number in the outer Kuiper belt, are believed to be the most undisturbed population in the solar system. And they have tested various theories to understand how they formed. They are scratching their heads still to a large degree, but they do believe that they represent objects that haven't changed much since the very beginning. Again, a happy accident of timing, as you see on this particular slide I just popped over here. This was on whether it was Sky and Telescope or Earth Sky the other day. I picked this up. The American Astronomical Association or Society latest meeting on October 6th, just a week ago, had this article in it about tight twins in the Kuiper belt, talking about equal mass binaries and the fact that they've just found JY31, which seem to be the very closest pair that are actually separate. And so again, we feel fortunate that much further in than the Kuiper belt, in the Trojans, we're going to be able to look at one of these equal mass binaries and see what we can learn from it. The one thing I haven't mentioned, and I want to go back and take a look at it for just a second, and that is the mission actually gathers data in what you might have wondered were rendezvous or something where they slowed down. But the fact is that nothing changes in terms of velocities. They don't try to slow down to match speed. And so I talked to Hal Levison about this last week. The encounter velocity is about 7.5 kilometers per second. And rather than try to stretch your imagination to what that feels like or seems like, I'll just say a couple things that it means. It means that when you go past Euripides, you spend about 10 seconds in the immediate close approach vicinity. When you go back past the larger ones, Patroclus, you spend about 20 seconds there. That doesn't sound like a lot of time, but relative to New Horizons, when it went past Pluto, it's quite workable. New Horizons encounter velocity was about twice this when it went past Pluto. And you've seen what kind of images and resolution and quality of measurements we've gotten in that. So we expect to get, as you'll see from the instruments and the fact that they are pointable, quite a lot of data, although, as Hal has pointed out, over a 12-year period of these first encounters with both swarms, we're going to collect about 24 hours of data total in that time going to these 6 objects. All right, so just trying to get close to finish up here. Donald Johansson was sort of a bonus we had toward the beginning. And so we've had this visit to a C-type in the main belt, a C-type in one swarm, and several P-types and a couple D-types there. And a ratio in terms of masses that we will see very great difference in mass from 1 to 160. And so lots and lots of diversity, not large number of visits with one mission. total of 7 objects that we will have close flybys of. Count it as 8 if you want to count Donald Johansson as well. And I want to now finish by telling you why we think that actually gathering the data will be very low risk. And you can probably guess that a way to lower the risk is simply to use very much proven instruments. And so you see the 3 principal instruments here. LRALPH, as you'll see in a minute, is actually 2 different types of instruments, LLORI and LTES on the right. And so each of these is actually a heritage instrument. In the case of LLORI and RALPH, you see them there flying on New Horizons, where they have flown and continue to fly and send back good data very successfully. And the third of these over on the right is a thermal emission spectrometer, TESS, which flew first to Mars in one of their orbiters over 10 years ago, and most recently is the identical instrument has been on OSIRIS-REx at Bennu. And so these are 3 very tested instruments, very proven, and lower the risk enormously. Here's what they do. In the upper right, first of all, is an artist concept of the overall spacecraft, and we'll talk about the configuration there with the solar panels in a minute. But in the 3 white boxes, you see these 3 principal instruments, LLORI, LRALPH, and LTES. You've now figured out that the naming came from putting Lucy, comma, in front of each of those 3 instrument names. And so we have the long-range reconnaissance imager for LLORI. If you look down at this little spectrum graph in the lower left, you'll see its coverage in the visible band there, a broadband but high spatial resolution visible imager. MVIC is one of the 2 instruments on LRALPH. The other one is LISA. MVIC covers both the pan and the specific spectral array of the mostly visible and maybe a bit of near infrared. LISA covers out into the near infrared and out into the middle, and TESS covers from the middle out towards the far infrared. And so a lot of good spectral coverage. And the antenna you see at the top there of this spacecraft is for doing radio science with Doppler measurements in addition for communications, but doing radio science with Doppler, which can be used then to calculate fairly accurately the mass of the objects. And then finally, TT-CAM is a really important imager that will find and then locate the centroid of and lock on and keep locked on while the spacecraft moves past each of the targets and keeps them centered so that the co-aligned instruments can do the most data gathering. And so here is the actual spacecraft in test configuration. You get a feeling for the size of it. The solar panels are not out here, so the 52 feet wide doesn't make sense. But the depth of it from the front of the antenna all the way through is about 9 feet. You can calculate, if you subtract out the diameter of the solar panels, that the actual spacecraft bus is probably only about 5 or 6 feet. The height is about the height of a 2-story building, 23.6 feet. And then very importantly, you see this silver canister in the middle of the spacecraft, which is the propellant tanks. And so in order to maintain these orbits and do the corrections and so on, you need propulsion, which they have on with these propellants. You see that roughly half the mass of the spacecraft is the fuel. And you may remember from Cassini that the whole question of mission longevity eventually comes down to, do we have any gas left? And so I didn't find out an estimate, but there's plenty on board there to last for a very long time past the primary mission. And then finally, the spacecraft has very manageable power needs. The furthest out from the sun, it only gets 504 watts, and it gets them from the solar panels. And so here in another picture of the spacecraft as it's being wrapped up for flight to be put into the fairing on top of the booster, you can see these black triangles, which are the stowed solar panels. They're only about 4 inches thick when they've been stowed. There's one of these identically symmetrically on the other side. And here's what they look like when they're opened up, with kind of a clever comparison to a good old TIE fighter there. You can picture Darth Vader and his special TIE fighter maybe, but at any rate, it gives you a feeling for just how big these solar panels are. If you drive down any of your streets and look at the side of a 2-story house, that's roughly the size of each of these solar panels. They're very big. And the reason they have to be big, as again, Janet mentioned earlier, is this is the deepest space mission yet launched that's not going to have another power source other than solar power. There is no RTG like Cassini and Galileo and Juno and all the others have had, because as you get out to Jupiter's orbit 5 times Earth's, and the energy goes down by the square of 5, you end up with 4% of the solar energy reaching them, as we have here at Earth. And so it's much more difficult to count on solar power. And that's why these are so big. And so we'll get another look here, finally, at those solar panels. Here they are in a clean room during a test to open them. As you'll see in a minute here, above the guy on the right there is a structure just above his head. And so as I put this into an animation, you'll see it start to open. And here comes the solar panel, just the way it's going to open once the spacecraft has shed its fairing in empty space, and they can pull these open. The mechanism here is strictly one for the lab, but you now see that it's like an oriental fan. Silicon solar cells, countless of them, it seems, mounted on a cloth backing. And they've calculated that it can take a lot of micrometeoroid hits and lose a lot of cells and still maintain the ability to generate sufficient power at that distance from the sun. And you may have noticed that structure above it, which always reminds me of a marionette or a puppet master. That is, of course, not part of the spacecraft. It's just what they needed to hold this in the lab. All right. So finally, the bragging rights that we've heard about from the Lucy team are that whereas all the NASA spacecraft that have visited the main belt previously have only gotten up close. Now, admittedly, in some cases, they've orbited, and in some cases gone down to the surface and gotten lots of up close science like that. But at any rate, they've only managed to visit 8 of them so far with multiple missions. And Lucy's going to visit 7, all within one Discovery mission. Okay, so lots of good science. We expect to improve our understanding of the Earth and planet formation once we visit these fossils. That's it. Questions?
If I may, I have one question regarding the solar panels.
Sure.
What kind of temperatures are they going to hit out there when they're in the belt? Well, with at the furthest distance from the sun, I guess.
I don't have a ready answer for you. Sorry.
All right, and no problem. I'm just wondering how it handles such such negative temperatures, being what they're made out of?
That's a good question, and I'm afraid I don't have anything to add.
All right, no problem. Thank you.
Mhm.
John, with all those flybys in a really short time frame, do they just have a huge team to analyze all those data? How's that going to happen?
I don't think it's a team that will change in size any more than Cassini, the Europeans, as well as the Americans, and the other missions that gather, a tremendous store of data. The research and development and the findings come out over a period of a number of years, usually after these missions. I'm sure there are some burning questions that there are asteroid specialists or theorists of the solar system formation that they are just anxious to get their hands on one or another of the particular target's data as quickly as possible. But for the most part, the NASA team, it's not like you have a NASA team that goes up and down. As you're aware, just like most of the government programs that spend a lot of money, they use contractors for these. And in the case of NASA, most of the research and development is done through universities or centers like the national labs and so on. And the teams get the data, and the conferences happen, and it just comes out over a period of time. Having said that, you may remember when I talked about James Webb not too long ago, they have an early science program and focus, and they have spent the better part, believe it or not, of 15 or 20 years vetting the teams. And the teams, in a way, since they started so earlier, were able to impact the design of some of the instruments in order to meet the scientific objectives, such that when they get the first data, they do have priorities on certain things that they're going to be studying and trying to get results on within the first, I would guess, couple of years or so.
I have a question. Is there anything planned during that 6-year interregnum from 2027 to 2033? Is there anything that they might fly by that might be interesting?
Not that Hal told us. It's a good question. And it may have an answer that's partly the answer to what Janet just asked, which is they got 6 years there with data from the first 4 asteroid targets plus a moon to start to work on. It might even make them smarter for what they want to look for when they get out there to Patroclus and Menetius.
Now, will it take a while to get the data back, like with New Horizons?
Not nearly that time. I mean, the light travel time, we're talking about a couple orders of magnitude less in terms of time. So, yeah, and we didn't get a lot of information about the subsystems of the spacecraft. I would like to have known, for example, what is the data rate and what is their routine for looking back to the Deep Space Network telescopes, or antenna on Earth, and delivering data. I don't know the answer to it, and it's a good question. I'm going to look into that. Thanks.
John, do you think there's any opportunity for us amateurs to see the satellite as it, or the probe as it flies by on one of these slingshot missions on to Earth?
With those, solar panels, I gotta believe that it would be a really nice target. Again, I'll look into that too. Some of the early, at the beginning of the space age, about 1960, I remember when they launched the Echo, basically inflatable balloons, just to get that large surface area to be reflected back so we could see them.
Yeah, I remember that.
Yeah, okay, good. I like to find peers.
I presume that the propellant that you are referring to is probably almost exclusively used as you want to insert into near orbit, so you get the right kind of slingshot effect. So I don't imagine you have any idea about like how many laps they have fuel for based upon that kind of assumption.
That's true. I do not have any idea. I gotta believe that with what was it, 1,400 pounds, 1,600 pounds of hydrazine and LOX, that it's way more than they would need for the course corrections for these several first orbits.
It'd be something if this mission extended more than one human lifetime.
Wouldn't be, obviously, the spacecraft's going to be up there much longer than many lifetimes.
Yeah, yeah.
But how long, and operating only on solar power, the instruments could still be powered, whether or not they're going to be able to keep it pointed and stuff like that. I don't know.
So I don't suppose they've mentioned anything about like after the primary mission window, do they have actual targets picked that far out, or is that something that they would make a course corrections to choose the targets they were going to fly by on a extended mission?
Yeah, I mean, the answer is almost certainly that yes, they do, because they wouldn't have come up with these 6 without having many more that they whittled it down from based on what certain researchers wanted to see.
Right.
Having said that, while Lockheed Martin and NASA astrodynamicists designed the orbits, and they did have to have targets in order to, do the exact timing of this. It would be very interesting to know how they handled those trade-offs, which, I mean, Hal Levison's been working on this for more than a dozen years with his team. And so they've done lots and lots of studies in order to come up with these final targets. All very good questions.
This isn't a question, but I was very impressed with the NASA website in terms of their outreach, and especially to kids. So for those of you listening who have kids and grandkids, take a look at the NASA website on this mission, and they have a whole host of videos directed right at kids to help them understand the mission, what it's doing. And because it's happening right now, it could be a way to interest them in space travel.
And that is much appreciated, Janice, because there was, in fact, one of the NASA talks recently that was strictly by some of the outreach people, not so much STEM as the younger people, to tell us about all those things. And I guess shame on me that I don't share as much of that, but it's not as much my primary focus. I will just admit that I like to talk to adult audiences better than younger ones, and so I don't grab onto the other things as much. But you're exactly right, and there are great outreach tools and so on all over the different NASA missions, not just Lucy. For grade school to, they're designed and put there for different age groups, and plenty of the ambassadors are actually teachers too in their full-time jobs. And they're the ones that tend to use these things more. I don't talk to schools very much, or I probably would get used to doing that as well.
John, would the Lucy satellite turn the whole satellite or just the sensors?
I'm going to go back to that slide, I think. Here we go. The gray platform, the platform is gimbaled, and I again didn't get as good a briefing on these things as I wish I had. It's not 3-axis gimbaled, and so I don't know whether it only has roll control or if it has some way of having roll and, pitch or yaw, but they can point it. I'm sorry, was that sufficient answer, or did I not get it yet?
Yeah, that's what I was wondering.
Yep.
So I presume then that the antenna and the solar array, those are going to always be pointed to where they need to be pointed. So the
Yes.
instrument will be aiming, and the craft will sort of stay in the orientation of collecting the sunlight and being able to communicate with Earth.
Well, I don't even know that, to be honest with you. I can picture that as, they may pass one asteroid where they essentially, if you will, lie on their back when they're looking at it, and then have to tilt forward in order to be pointing back at the sun, which is effectively pointing back toward the Earth for communications as well. And in another, they may lie on their stomach, for all I know.
Yeah, I guess if it's they're collecting data for like less than a minute,
Yeah.
they could afford to be out of alignment with the Earth and the sun for less than a minute.
Right. And again, we weren't briefed on the power subsystem, but I wouldn't be surprised if there isn't a battery in there somewhere.
So if the flyby is that brief, that means that every command has to be pre-uploaded. So it'll be a lot like New Horizons, where you have to send the whole observing plan up to the satellite in advance, and by the time you get the first data back, it's already over. Is that right?
Absolutely. And Cassini, you may remember when it went by Titan, was the same way. I mean, it had a visible IR instrument that did, a certain kind of swath, and it had its SAR, its synthetic aperture radar, and at different points as it came down towards the surface in what had been, they weren't steering the spacecraft. They had long since programmed that orbit. And as you said, they had long since designed and uploaded the command in order to turn on and off. And in the case of Cassini, the entire stack, and I've forgotten right now, but it seems to me it was like a 3-story tall stack of instruments, all that were hard mounted on it. There was no gimbling of anything at all in that case. So they had to continually move that whole moment of inertia around, if you will. It was extraordinary what they did, but they didn't do any of it in real time. It's all pre-programmed and commanded.
I have a related question to that. A couple of years ago, we had a presenter, Steve Connard, very similar name to yours. He worked on the New Horizons mission, and when they did the flyby of that second object, they actually had to do follow-up observations in order to refine the orbit, because they had to have everything pre-programmed in advance, so they have to know exactly where that object is. But do you know if they're going to have to do any similar observations for these objects to refine the orbits?
I can only imagine that since they have observed, named, targeted, put into the IAU catalog and track, on a regular basis and update the orbital elements for these objects, that they know that they will, continue to update things as they go through the 3 years out and 3 years back in, that anyway. They have plenty of time to do that sort of thing, and I'm sure that they will update and check on and then update the orbital elements in order to do the pointing commands, so on.
I'm wondering if that's something the amateur community could help with, because in the case of the Pluto, or not Pluto, but the second flyby that New Horizons did, they actually needed occultation timings in order to get the position nailed down much better than they could get just by imaging.
I suspect that, while I'd love yet another job for amateurs, these are so much closer, and the orbital elements will be so much easier to acquire. The objects will be so much easier to acquire. We're talking about a factor of 10 in terms of distance. From between the two. I don't think that they'll need to do that kind of special thing in order to nail down these target locations.
If I recall, during the animation that you showed, it had the appearance that these objects in these two swarms were sort of circulating or moving relative to each other. Was that an accurate representation, or their relationship to each other, is that pretty static?
It's not static at all. We talk about the Lagrange points as if you can just go and set your coffee cup, your coffee mug there, and it'll stay there. It's not quite that stable, but that's not the reason, really. The thing I had to keep reminding myself of when I was looking into this for some period of time was these are not in orbit around anything except the sun, just like the Earth is. And so every one of them is an individual solar orbiting object. And they're not big enough to attract each other away or closer or anything like that. They aren't out there deflecting each other unless by chance, as happens at least once a year, we believe, in the main belt. And it's an interesting thing, but we say that with all these collisions and collisional families in the main belt, well, you think, well, how could that be? But the fact is, if you only have one a year, it's been 4 billion years. So that's a lot of collisions, creating a lot of smaller objects in the main belt. And again, these have been out there, and there's over 1 million of them, we believe, and they've been out there for 4 billion years as well. And so the fact that we've only found one for sure collisional family so far is, my guess is we'll find more at some point, but the point is that they're much less likely to run into each other. It's a much denser swarm, if you will. And each of them, again, is in its own elliptical orbit. Elliptical with an eccentricity that's close to the same as Jupiter's, and different than each of its neighbors. I mean, they're all in their own unique orbits in a swarm, but you can see them kind of moving relative to each other because as they go around in their 12-year period, that's just the way it is with regard to the neighbors that were there the last time they came around that 12 years. They're going to change.
So it sounds like what you're saying is that the gravitational force on the sun of each of these individual objects is still much stronger than the gravitational force in between them.
Oh, yes.
Yeah.
Yes. Right. Good questions. Thank you.
Do we have any questions from YouTube? Do you know, Jeremy?
No, I'm not seeing any there.
Okay. Any other questions from our audience here?
One question. One of the early slides showed the proportion of the 3 different sorts of composition for the asteroids, for 3 different size ranges. And there was one type, I think it was the P-type, that was quite common for large asteroids and small ones, but not for middling-sized ones. Why?
Okay, ask the question again, please.
Yeah, you look at those 3 charts for the proportion of the 3 spectral types for different, what appears to be for 3 different size ranges of asteroid. Why you have small P-type asteroids, large P-type asteroids, but no middling-sized P-type asteroids?
And I'm just staring hard to make sure there is no orange there. I believe that question got asked in one of our sessions with Hal. I'm going to go back. I have the transcripts from those. I don't remember the answer. That's a very good question. It's a very good observation. I don't know. And I'm going to go ask. And Jeremy, may I ask, I don't know if you or anybody's taken notes. There were 2 or 3 questions now that I would like to follow up on. If you, I'm lazily not putting pen to paper here, so I've already forgotten one or two of them.
I'm trying to remember which one. So was it about the bandwidth for communications? Was that one of them?
Yeah, probably mhm. Yeah, the data.
And there was the one about the mid-size P-type asteroids, or why they're not apparently represented.
Right.
Trying to remember, was there another one?
Somebody had a question about the steering of the satellite and the instrument head, whether you could do all the observing just by swiveling the instrument head and keep the solar panels and the radio dish pointed at the sun and Earth, or whether occasionally you had to flip the entire satellite.
That is a good question. I'll look into that. Yep.
I guess maybe another one, we didn't state it possibly this way, but how much of the fuel do they anticipate needing for maneuvering the space flight just over the primary mission?
Yeah, really. 80%? What?
Could you ask the question again? I was writing down the other question.
Yeah, for the primary mission completion, how much of the hydrazine do they expect to have to use?
Oh, that's a good question. I'll find out.
Guessing they're probably going to use a lot of it very early on, right? Boosting from the low Earth orbit into the right into the heliocentric transfer orbit, and then doing the 2 Earth flybys. Right, those are the biggest delta V's, right?
Well, the intent is to use the Earth gravity assist, and so I couldn't tell you. I'm going to ask, because my assumption is that they've designed it in such a way that they can boost it mostly with the gravity assist. I mean, that's what we do over and over again, as we did when we went out to Cassini over whatever it was, a 9-year period or something, out to Saturn.
I presume all the maneuvering would be perpendicular, tangential to the direction of the aircraft. You want to move it sideways so that you get the right insertion into the orbit, or the near Earth orbit pass that you want to do. You're not using it to accelerate, but to hit your sweet spot.
Was that a question?
Yeah, I'm just saying that's my assumption.
Okay. Well, I've certainly enjoyed this. Any more questions?
Thank you, John. This was so interesting. And I was thinking of the how it compares, or it just blows my mind how interesting this mission is. Think of the other major space news we had this week, William Shatner going into space, and can't really compare the two.
I certainly hope not. I mean, I did watch the original Star Trek when it was originally on. Even though nobody asked, I'll tell you my opinion of these various recent
but the tourists,
what do we call them? Commercial launches of space of Earthlings that can afford it. I think it's a wonderful thing. I think it's great and it's interesting as can be, and it hasn't the slightest relationship to being an astronaut.
Right.
Which really troubles me, because I know astronauts personally, and that really, you know, when they come home from these times and give each other astronaut badges and things, I kind of wonder what the astronauts actually feel like. Anyway.
Well, I thought there was a move to change the definition so they wouldn't really be able to do that.
I've been watching for it. I haven't seen it. So if you see it, let me know. I'd like to see that. I wrote a letter to the editor about it and suggested that they actually poll the whole community of astronauts and let them decide what they think the name should be. Space tourists is a little silly, but wealthy guy on a really fun amusement ride might be closer. I don't know.
They can come up with a clever acronym for that, maybe. So
That's right.
But
Now,
we have-
I
we have-
presume that the launch angle is going to be probably out over the ocean to take advantage of the rotation of the Earth. So it's not going to be coming overhead up here in Pennsylvania.
Never.
Yeah.
I mean, you mean during the initial ascent?
The initial ascent, yes.
No, I mean, that's why there's Vandenberg to launch into polar orbits, and there's Kennedy, and now in Maryland to launch more equatorial named azimuths. But you want to be on the equator launching directly east if you want to take advantage of most of the rotational energy of the Earth.
Because we've seen Wallops launches up here.
Right. Yeah.
But, you wouldn't see one from Cape Canaveral.
Oh, no. If you did, something went very wrong.
Very bad.
Okay,
And the rain
Jeremy,
safe,
I
and the
guess-
rain safety officer will not be employed any longer.
I guess we have no more questions, so I guess we can say goodbye to our YouTube audience.
Okay. I have to log out and log back in again. All right. It shouldn't affect anybody else, but I'll be back in just a second.
Thank you so much, John.
You're welcome. I
Just-
enjoyed it.
Just really, really great science and presented in such a nice way, understandable way. We really appreciate the presentations that you put together, the ones that you've given for us. Thank you so much.
See you guys soon. Hopefully to see you physically one of these days soon.
That would be great.
Take care.
Thank you. Bye-bye.
What's what? Clifton? Yeah, it's north, it's near the bridge.
All right, I'll be back here.
Right there. You want to take one of the, no?
Take what? No. No, because